Hello, this is Joseph, and this is my AP problem that I'll be explaining for Gauss's law parallel plates. As you can see, this is a 1980 E2, if you want to pull it up for the reference. Okay, so the problem is a parallel plate capacitor consists of two conducting plates separated by a distance of d. The plates are considered pretty large, so the effects of the edges may be ignored, so pretty much considered to be infinitely wide and long. The two plates have an equal but opposite surface charge per unit area, and the charge on either plate resides entirely on the inner surface facing the opposite plate. Okay, A. On the diagram below, draw the electric field lines the electric field lines in the region between the two plates. All right, so all right, it's 1980 E2. Problem A. We got the two plates. And now, since we ignoring the edge effects, let's see, they're oppositely charged. Two plates have an equal but opposite surface. So assuming the top one is positive and the bottom one is negative. Do they say which one it is? They do. The top one is positive and the bottom one is negative. So the electric field lines in the region between the two plates would simply be like this, from the positive plate to the negative plate, ignoring the edge effects. Okay, B. Put that here. By applying Gauss's law to the rectangular box whose upper surface lies entirely within the top conducting plate, as shown in the following diagram, determine the magnitude of electric field E in the region between the two plates. Okay, so let me just draw that out. We got they drew it in a bit of a three-dimensional way. I'm just gonna draw it the same as the A. Actually, forget that. I'll draw it like them, with the 3 dimensions. Okay, so you got your two plates. Positive one up here. Let me just write that there. Negative one down here. So the electric field lines would be from the positive one down to the negative one. Okay, so it's telling us to use Gauss's law with the rectangular box with the top surface inside the top plate and the bottom face inside, well, between the two plates. Okay, since the top face is inside a conductor, and we know that in the electrostatic situation there can't be any electric field strength or flux density inside of a conductor, the summation of, well, the total electric flux in the top face would be 0. So we don't have to add that to the total sum. And so the top face is total of 0 electric flux. Now the side faces, do they say it's perpendicular within the shown term of the magnetic field? Okay, they don't specify if it's got to be perpendicular. But I mean, okay, so I'm just gonna set it perpendicular because I mean, that's how you would do it. Because by setting it perpendicular to the plates, the cosine of they would be they're parallel to the electric flux, but like parallel to the electric flux means perpendicular to the two plates. So the dot product of the sums. I should probably write this down actually. So Gauss's law. I'll write it over. Let me see. Let me write it over a bit. Charged enclosed over epsilon naught. Well, in this case, it's about epsilon naught, assuming this is free space, equals summation of electric field strengths dot product, which pretty much is multiplied by cosine theta times the total area. So this would just equal, since this is all they mention considered very large. Do they say it's uniform? The plates may be considered to have equal. Okay, so they say it's an equal but opposite surface charge per unit area, and that's a constant. So yes, it is uniform. So it would just be the electric field at all the points on whatever surface you're using, cosine theta times the total area. And since all of these four faces of like the side, these four faces of the rectangular box are all perpendicular to the plates, they would all be E times 0, because cosine of 90 degrees is 0 times area. So this would be 0. So we can also rule out everything from the parallel faces of the rectangular prism or box. So really all that we're left with is this bottom face. And this bottom face is between the two plates. So we got the electric. Okay, so we got the electric. Make sure it's like focused. It's a bit blurry. Okay, so we got the electric flux running through like this. Yeah, okay. So what we want to do is find the charge enclosed by the entire rectangular prism over epsilon naught, and assuming this is free space, equals, and since the only face that we know has any electric flux is the bottom face, we can just say it's the electric field at any point on the bottom face times the area of the bottom face. Let me just make sure. Yeah, okay. Okay, so the charge enclosed would be charge enclosed. They say it's the two plates have an equal but opposite surface charge per unit area of, sorry, it's a bit out of focus. That Greek symbol, which I think I want to say, I forget the exact name of that Greek symbol, but it's that. So we got the charge density is that symbol, and whatever the area is. So we got charge enclosed would be the charge density times the area of the bottom face. And the reason it's the area of the bottom face is because Well, we know this rectangular prism is only enclosing. Well, it's only touching the top plate because the bottom face is between the two plates, and it says the top plate is inside the top plate. And since the plates are both conductors, um, all the charge would be at the very edge to make the electric potential within the conductors zero, as they should be, which is also the reason why the top face has a total electric flux of 0. Okay, so we got the charge enclosed, total charge enclosed would equal, okay, yeah, the area of the bottom face, because obviously it's a rectangular box, so the area of the top face, which is hold up, the area of the charge, yeah, sorry, the since the charges are all on the very edge of the plate, and it says the charge density is per unit area. All we really have to do is multiply that charge density per the unit area times the cross section of the rectangular prism, which, since it's a rectangular prism, would just be the same as the area of the bottom face. So charge enclosed is the charge density per unit area times the cross-sectional area, which is the same as the area of the bottom face, over epsilon naught, which if, like, assuming this is free space, equals the electric field or flux density times, well, no need for dot product there. Well, actually, oh yeah, they're actually yeah. I mean, this is perpendicular, so either way, really fine. Area of bottom face. And as you can see, you can divide by area of bottom face by each side, canceling that variable out. So what we're left with is the electric. My computer went off for a second. What we're trying to find again? By applying the Gauss's law. Okay, the magnitude of electric field would simply equal the charge density for the unit area, that Greek symbol that I forgot the name of. I think I've been drawing that Greek symbol actually a bit wrong. Yeah, like that. Move it over a bit. Over epsilon naught, assuming free space. Okay, so determine the magnitude. All right, so yeah, assuming this is free space, and given the charge density per unit area is that Greek symbol, the electric field at any point between the two plates is this. And the reason it's any point between the two plates is well, I explained this in the original Gauss law video, but I'll explain it again. Since we used Gauss's law, this final electric field, it depends on the charge density and the permittivity of the material or the free space between the two plates. And since we didn't really specify like where exactly this bottom face of the rectangular prism / box has to be located, we just specified that it has to be between the two plates. So really, since there's no variable of like location of this plate, except that like it has to be between the two plates, any point really that is in between the two plates, ignoring the side effects that we're told to ignore, will have the same electric field magnitude, which is the charge density per unit area over the permittivity, epsilon naught in this case. All right, so let's be C. Oops, let me just separate. Whoops. No. Okay, C. In terms of given values, find the difference in potential between the two plates. Okay, so that should be pretty simple. So the electric potential is pretty much the energy per charge, which in other words is the voltage. For this problem, however, I'm going to consider it as energy per charge, or work per charge. So it would be the force, or no, I probably shouldn't write it as force, but I'm going to write this first down. The change in energy is defined as work equals force times distance dot product. Well, I mean, in this case, we don't really need dot product because we know it's well, it's a line with it, so no need for cosine or anything. It's the force times the distance the force is applied across. So that would be the change in energy. One second. Shh. Sorry. Okay, so the work is force times distance. In this case, the force is the electric field magnitude or flux density, which we solved for in the previous part of the question. I'm going to write that as just the electric field magnitude for a second and the distance. Okay. And as I explained in the previous part, the electric field magnitude is the same at every point in between the opposing faces. One second, sorry, give me a second. Sorry about that. So where were we? All right, so because the field magnitude is which we're saying is the force, is constant at every point in between the two faces, this force would be constant the entire way, or the electric field magnitude. So we can just write that as what we solved for the previous problem, which was that Greek symbol that I forgot the name of, over epsilon naught, since we're still assuming this is free space in between the two plates. Now for the distance, they tell us the distance between the two plates is d. They use a capital D. Okay, so capital D. Yeah, and that's it. That's really it. It's just the electric field magnitude times the distance between the two plates is the electric potential between the two plates, or as they word it, difference in potential. All right, last problem. D. A dielectric is inserted and fills the region between the two plates. Is the electric field greater than, less than, or equal to the electric field when there is no dielectric? Describe the mechanism responsible for this effect. Recognize the plates are not connected to a battery. Okay. Okay, so do we have to find any values or? Okay, no, okay, so A dielectric is an insulator, so it's not gonna change the charges or anything. And what it does is it, you know, in simple terms, it strengthens pretty much the electric field because the the charged plates and their electric flux between them is polarizes, gives electric polarization to the material inside the dielectric, and the strength of that polarization, well, the strength produced by that electric polarization depends on the material, and that's where their permittivity comes into play. And yes, so I'm assuming this dielectric is I mean, if it's doing the job like it was meant to be for, it should definitely be greater than when there is no dielectric. Otherwise, that'd be a pretty useless dielectric. Field greater, so the electric field would be greater. How much greater, it would depend on the permittivity of the material that the dielectric is made out of. Okay, less than or equal. Describe the mechanism response. Okay, so yeah, I already pretty much described it, but that's just the thing that makes the electric field stronger is created by the electric flux. Instead of like just communicating directly to the other plate, it produces electric polarization of the material inside the dielectric, which kind of like a magnet, except that's magnetic polarization. This is electric. It produces it aligns pretty much all it aligns the material, the molecules inside that dielectric to in the direction of whatever the electric flux is. In this case, it's just from the positive plate to the negative plate, and helps strengthen the electric field. So yeah, that's my explanation. Get a full picture of it. Why is it not focusing? All right. That's 1980 E2 for parallel plates solved using Gauss's law. Thanks.